This conference will now be recorded.
A universal good afternoon to everyone. Self-belief and hard work will always earn you success. I hope all are doing well. I'm Anita from ECE Department of Loyola Institute of Technology. I welcome you all for this wonderful webinar on random process and noise characterization in communication systems. If the only prayer you said was thank you, that would be enough. Now I call upon Noble and Malati to lead us with a word of prayer. Over to you, Noble.
Thank you, Anita. Reading from the book of Colossians, chapter 2, verses 2 and 3. My goal is that they may be encouraged in heart and united in love, so that they may have full riches of complete understanding, in order that they may know the mystery of God, namely Christ, in whom are hidden all the treasures of wisdom and knowledge. This is the word of the Lord. Thanks be to God.
Lord's Prayer. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from evil. Amen.
Thank you, Noble and Malti. Now I call upon Miss Josh Janita to deliver the welcome address. Over to you, Josh Janita.
Thank you, Miss Anita. Good evening to everyone gathered here. I hope everyone is safe and doing good. It's my pleasure to extend a cheerful welcome to you all on behalf of Lila Institute of Technology Management, Administrator, Principal, and Vice Principal and HOD of EC Department, Dr. Nalini Joseph Ma'am. We wholeheartedly welcome all the participants for this webinar. On behalf of the department, we the coordinators welcome our speaker of today's session, Dr. K.R. Shanti Ma'am, Associate Professor in the Department of ECE, KLN Engineering College. It's my pleasure to extend a cheerful welcome to you, ma'am. Your presence makes us very happy. I'm sure we'll be able to enrich your knowledge by this webinar on random process and noise characterization in communication systems. Thank you, ma'am, for accepting our invitation even in your busy schedule. We welcome you wholeheartedly for the webinar. In this context, I welcome all the coordinators of this webinar, faculty members of ECE, and professional friends to make this happen. Dear participants, once again, I welcome you all for this wonderful technical day. Thank you. Over to you, Miss Anita.
Thank you, Josh Janita. May I call upon Miss Shiny of EC Department to introduce our speaker. Over to you, Shiny.
Thank you, Miss Anita. Good evening to everyone. I am Shiny Sujita from the Department of ECE of Loyola Institute of Technology, and I take immense pleasure in introducing today's resource person, Dr. K.R. Shanti, Associate Professor of ECE Department, KLN College of Engineering, Madurai. She has completed her undergraduate degree in Electronics and Communication Engineering in the year 1989 in Tyagaraja College of Engineering, Madurai, and she did her postgraduate degree in the year 2010 in KLN College of Engineering, Madurai. Also, she has done her PhD in the area of cognitive radio networks in Anna University, who is now presently working as an associate professor in KLN College of Engineering. She has 18 years of teaching experience in engineering colleges and 5 years of industry experience. She has published about 18 papers in journals and various conferences in the area of wireless communication and attended almost 53 faculty development programs and workshops. She has also acted as a judge in technical paper presentation in various international conferences and have prepared monographs for various courses such as communication theory, digital communication, wireless communication, communication system laboratory, and linear integrated circuits laboratory. She is also a gold medalist in NPTEL online certification course on principles of communication systems and has produced 100% results in the paper Optical Communication Networks, Electronic Circuits and Linear Integrated Circuits. It's really wonderful to have such a knowledgeable person with us to give us a webinar on random process and noise characterization in communication systems. We welcome you wholeheartedly for this webinar. Thank you, ma'am. Over to you, Ms. Anita.
Thank you, Shiny. The struggle you are in today is developing the strength you need for tomorrow, and there are no shortcut to any place worth going. In our most awaited session of the day, let us go to enhance knowledge in random process and noise characterization in communication systems. Now I request Dr. Shanti, Associate Professor, Department of ECE, KLN College of Engineering, Madurai, to take over the session. Over to you, ma'am.
Yes, thank you. Good afternoon, all. Am I audible?
Good afternoon, ma'am. Yes, madam. Good
Good
afternoon, ma'am.
afternoon, ma'am. Good afternoon, all. Thank you for your kind introduction about me. And I thank Dr. Nalini Joseph, ma'am, Vice Principal and HOD EC Department, for giving me this opportunity to present in this webinar. Thank you, ma'am. So now I'll go to the presentation. So are you able to see my presentation?
Yes, ma'am.
Yes, madam. Yeah, full
Okay.
screen has come. Okay, ma'am.
Okay. Thank you. So the topic today is about a random process and noise in communication systems. So to know about a random process, so you should know what is meant by a random signal. So first we'll deal about your random process and then about noise. So you should know what is meant by a random signal. You're having two classes of signals. One is a deterministic signals and another one is a random signals. So deterministic signals, you know that it is can be determined. It is completely determined, then it is a deterministic signal. And a random signals is a signal which you can't predict its value. That is, you can't predict the value of the random signal in advance. That is a random signals. So if you take an example of a deterministic signal, you can take any sinusoidal signal. So that sinusoidal signal, it will have, you can specify it by means of using its amplitude, frequency, and phase. All right, then it is completely specified, it is deterministic. And if it is not able to specify a signal, then it is a random signal. Example of a random signal in radio communication system, if you take a received signal, the received signal, you are transmitting a signal, and then in the receiver, you are receiving a signal. And in the receiver, the received signal will come with a message as well as with noise, interference, and other things. So if you take your message, suppose you are transmitting your voice signal, right? That voice is random in nature. So it is a random signal. Your information is random. And it may affected by the nearby interferences, which may have some electromagnetic interference in the nearby channels. So that is also random. And it will be affected by noise in the receiver due to random motion of electrons. That is in the receiver, it will be affected by thermal noise. You would have studied about that. So that is also random. So your total, the received signal will be random in nature. So you have to study about random signals in order to well understand your communication system, right? So to describe this random signal, it cannot be specified, but it can be described by means of its statistical properties, right? So you are using the probability theory as a mathematical tool for in order to describe the statistical characteristics of your random signal. So what is a random experiment? The random experiment, the outcome which is random, the outcome of an experiment which is random, we're calling it as a random experiment. One minute, I was not able to move my slide.
Ma'am, press down key, madam.
Yeah, down key only I am doing.
Then you press right key.
1 minute.
Ma'am, it's coming, ma'am, now.
Yeah, yes. Okay, sorry. See, actually the screen is hiding my presentation.
Madam, as I told you, that opposite arrow marks there in the GoToMeeting, no? You press that, it will go off. Shanti,
Okay.
ma'am?
Yeah.
Opposite
Now,
arrow mark.
yeah. Okay.
Yeah,
Are you able to see that slide?
yeah. Only your slide only is seen, not the GoToMeeting screen. No problem.
Okay. So if it is the outcome of a random experiment, your mapping, you should know about what is a random variable and what is a random process, which is the most important thing. So the random variable, the outcome of a random experiment is mapped to your real number, that is a random variable. And if the outcome is mapped to a random waveform, that is a function of time, it is a random process. So first we'll study about random variable, then we'll go to random process. But usually in communication system, we'll be dealing with mostly random process. So if your possible outcomes, you are constituted. All the possible outcomes constitute a random space, right? So usually in probability theory, they will be telling the two examples, tossing a coin or rolling a die. So tossing a coin, the outcome can be head or tail. And if you are rolling a die, the outcome can be 1 dot, 2 dots, 3 dots, like that up to 6. So the sample space outcome you are in the diagram, if you see, outcome it is W1, W2, W3, W4, and it is mapped to your real number, capital X, X of W1, X of W2, that is your random variable. And so the random variable is denoted as capital X, right? So if you know, you should know about the probability in order to understand your random process and random variable. So the probability is used to quantify your likelihood or chance. That is, it can be interpreted as a relative frequency. That is, suppose you are, for an example, if you are tossing a coin and you are 10 times and you are getting your head as 5 times, then your relative frequency is 5 by 10. So as you, the number of conducting that experiment, that is number of tossing a coin, you increases, then that value, you can call it as the probability that the head event occurs, right? So it is nothing but the relative frequency, and you are assigning a value between 0 to 1 to quantify that relative frequency. So that probability value can be from 0 to 1, right? So higher probability indicates that the event or probability is more, that is, it is more likely to occur. So it is expressed in terms of random variable. The probability that X is equal to K is 1 by 6. Then example of rolling a die, that is equal probabilities. And another example, you can take the length of the part, any part, that the probability that a random variable X lies between chain 0.8 and 11.2. This is an example. It is 0.25. So it is specified like this. So the properties of the probability, you know, the sure event, if it is sure that the event will occur, then the probability is 1, and the probability value will always lies between 0 and 1. And if you're having mutually exclusive events, then the probability of all the mutually exclusive events is sum of the probability of individual events. So coming to the random variable, it can be a discrete or a continuous random variable. So if the random variable is mapped to a set of finite set of real numbers in an observation interval, right? You are mapping the random variable to a finite set, which is a discrete set. Then it is a discrete random variable. And if you are mapping a random variable to a continuous set in an observation interval that is continuously varying. For example, it can be a pressure, it can be a temperature, current, voltage, like that. There are examples for continuous random variables. And if discrete random variables, example, you can take the scratches on the surface. That is, it is countable, number of scratches, or number of defective parts, or number of transmitted bits, error bits, like that. So that is a discrete random variable. So in order to for description of this random variable, you should know about the distribution function. There are two distribution functions. So the distribution function is nothing but it tells all of its possible values along with their associated probabilities. That is, you're having two functions. So the most important one when dealing with random process, you should be familiar with this two functions, that is cumulative distribution function and the probability density function. The cumulative distribution function CDF is denoted with a capital F, and the probability density function is small f. So the cumulative distribution function F capital Fx of x is denoted as a probability that x is less than or equal to x, and its value of minus infinity 0 and plus infinity is 1. And the probability density function is given as the derivative of your cumulative distribution function, right? From the probability density function, you can find the cumulative distribution function by integrating it and by using a dummy variable, that is small fx of y dy, integrated from minus infinity to x. Then you will get the probability distribution function of that random variable. So the random variable, if we want to find the probability of a random variable x that lies between the interval a to b, you can find it by integrating the probability density of the random variable using the dummy variable y in the interval a to b, right? So if you see the example, I think you will understood it better. So as for you should know that it is, you are having two distribution function. One is cumulative, another one is probability density function. And the derivative of cumulative distribution function is the probability density functions. So for discrete random variable, the probability density function is equal to the probability that x is equal to that value. For example, if you take this random variables 0, 1, 2, 3, 4, and 0 is having a probability of 0.6, 1.29, like that, 2.04, like that it is given. So the probability is plotted with random variables that gives the probability density function or probability mass function. Both are same, right? So if you go for the cumulative distribution function, this is the cumulative distribution function for the same example. So it is the probability that the random variable x is less than or equal to x. So for the probability 0 is 0.6, and then the probability that x less than 1, it is, it is 0.65 plus 0.29. So approximately it will be 0.94. So it is 1, you are having 0.94 as a cumulative distribution function. Similarly 2, 3. So it will be added. That is, the probabilities is getting added. That is the cumulative, right? So the total probability, the final probability will be 1. Right? That is a cumulative distribution function. So for the cumulative distribution function, x is equal to minus infinity is 0, and x is equal to plus infinity, then it means its value is 1. So this is another example of the probability distribution of a random variable, so that you can understand it, what is meant by probability distribution. That is probability density function. And if you are having, if you are assuming a random variable x as a number of tails in two tosses of a coin, that is, you are tossing a coin twice, and what is the number of tails? So if you toss a coin twice, you can have four choices, that is head head can occur, or head tail, or tail head, or tail and tail can occur. There are four combinations. So the probability that number of tail is 0 is, it is 1 by 4, and the probability that number of tail is 1, you are having 1 by 2, number of tails 2, it is 1 by 4. Right? While the number of tails 0 is 1 by 4, you are having four choices. In that, there is no tails, means it is the combination HH, head head. So it is one combination, so it is 1 by 4. Then the probability the number of tail is 1 means you are having two choices, that is head tail or tail head. So 1 by 4 plus 1 by 4, it is 1 by 2. And the probability that number of tail is 2 means you are having one choice, that is tail tail. So it is 1 by 4. So if you are plotting that probability with this random variables, all the possible values of the random variables with their probabilities, that is called as a probability density function. So that probability density function and cumulative distribution function will be used for in describing your random process. So you should understand this basic concepts. And this is a probability density function of a continuous random variable. So your random variable x lies between a and b. The probability can be found by integrating your probability density curve f of x in the interval a to b. Then you have to know about the moments of the random variables, that is mean and variance. So the mean of the random variable is nothing but the expectation of x. That is, in order to know about the average information of that um, outcome of an experiment. So having an experiment, that outcome is mapped to a random variable. So to understand about the average information of the outcome of that experiment, you are finding the mean, that is expectation of x. It is given a sum of summation x into that probability. And another moment is variance. The variance of x is equal to expectation of x minus mu the whole square, that is mean square value of that random variable, how it is deviated from the average value. X minus mu is the deviation from the average value, and the square of that, it is expectation of x minus mu the whole square, that is denoted as variance of x, and it is symbol is sigma square. The square root of the variance, we are calling it as a deviation. These are all the basic things we should know: what is the mean of the random variable and what is the variance of the random variable. Similarly, this is the mean and variance of a continuous random variable. This is for discrete, you are summing up, and for continuous, you are integrating it. That's all the difference. So the continuous random variable mu is equal to integrate x fx dx minus infinity to plus infinity. Similarly, variance is integrating x minus mu square fx dx. So important continuous distributions, you will have that a Gaussian distribution or normal distributions. And if the probability density function is given by this 1 by root of 2 pi sigma exponential minus x minus mu the whole square divided by 2 sigma square, x lies between minus infinity to plus infinity. This is an important distribution which is used in communications. This distribution, you will be calling it as a Gaussian or normal distributions. And mu is called as the mean of the random variable x, and sigma square is called as the variance of the random variable. And the probability density function of the random variable is given by this equation, right? This is an example of that distribution of various mean values, mu is equal to 5, mu is equal to 50, and for various variance values, right? So this is a uniform distribution. Another example for a continuous distribution. This is one distribution Gaussian, and another one is uniform distribution. It is that is the random variable. The probability that the random variable occurs is having the same probability in the interval a to b. Right? It is having the same. That is the meaning. It is having the same probability in the interval a to b in equal intervals of time. That is the mean. So it is the uniform distribution of the random variable. And if you want to find the cumulative distribution function, you can integrate it using a dummy variable from x to infinity. Then you will get it as x minus a by v minus a. That is the cumulative distribution function. And it will be, the graph will be like increasing slope. Then if you are having two random variables, then you have to know about a joint distribution. So joint distribution, you are having two random variables, x and y. So the probability that x lies less than x and y lies less than y, that is given by the joint distribution function. Similarly, joint probability density functions, and you are having the properties. And you are having an important property that if x and y are independent random variables, then that the probability density function can be separable. That is, joint density function of x and y is given by multiplication of individual density function. Fxy xy is equal to fx of x into fy of y. And if they are uncorrelated, it means x equal to expectation of y and y equal to expectation of x into expectation of y, if the two random variables are uncorrelated. All right. So this is a joint, and if they are identical distribution, that is all having same distribution, then that random variable you are calling it as IID, that is independent identically distributed random variables. So this is the graph showing the joint distributions with a diameter as x and thickness as y. So if you want to find that the probability that the diameter lies between A and B and the thickness lies between C and D, you have to integrate the probability curve f of xy in that interval. Right? So that is a joint distribution. So now we will next move on to the random process. So which is the most important thing. If random variable means outcome, again I am repeating, random variable, outcome of a random experiment, you are mapping to a real number with a probability rule. That is most important. Similarly, the random process is the outcome of a random experiment is mapped to a function of time, right? So if you take this sample space consisting of outcomes S1, S2, and the outcome S1 you are mapping to a waveform x1 of t, and S2 you are mapping to a waveform x2 of t, and Sn you are mapping to a waveform xn of t, then this is a random process. So each x1 of t and x2 of t you are calling it as a sample function of the random process. X1 of t denoted as a sample function of the random process. That is x1 of t, it is the outcome when S1 comes, right? That is mapped to a waveform x1 of t with a probabilistic rule, right? So that ensemble of the sample functions, that is a random process, and random process you are denoting it as capital X of t. So for a fixed time, the random process is a random variable. For example, if you take the time tk, x1 of tk and x2 of tk, xn of tk, it is denoted in this values x1 of tk, x2 of tk, and xn of tk. These are all the random variables. That is, if you observe the random process at a particular time, it is nothing but a random variable. So that's what it is explained in this slide. So some sample functions of the random process, if you take a sinusoidal signal represented as some a cos omega t plus theta, and your theta is uniformly distributed. Theta is a random variable, phase is distributed. So theta is 0 or theta is pi by 4 or theta is 3 pi by 4. This is the sample functions of a random process. This right hand side in this diagram shows this is another example of a random process. So this is another example. If you take a same thing, but with amplitude is changing. Amplitude is a randomly changing, and the amplitude is changing with a binomial distribution. So this is an example of a random process with amplitude changing, right? So number of outcomes, that is number of trials n is equal to 5 with a probability p is equal to 0.5. So these are some examples of a random process. So in the real time, usually you will be dealing with communication signal, a voice signal, a television signal, a video signal, or a data signal, computer data containing ones and zeros. So any signal, in order to describe that statistical characteristics of that signal, you are going for random process. That is the outcome you are mapping to a waveform. So then another important thing about the random process is stationary process. So the stationary process means if you take a random process x of t and you are observing the random variables x of t1, x of t2 up to x of tk. Let us assume you are taking the random variables at time t1, t2 up to tk. This is the random variable obtained by observing the random process x of t, and then the joint distribution function of the random variables So the joint distribution of the random variables taken at some other time, tau. So you can take it as t1 plus tau, t2 plus tau, tk plus tau, like that. So the if both are same means then for all time shift and for all k and for all possible choices of t1, t2, tk, it means it is the stationary process. So stationary process you should understand that is the statistical characteristic is independent of time. That is the meaning. You are observing the random process at some particular time. You are taking the collections of random variables and other probability joint distribution function பார்க்கிறோம். And you are finding that observing the random process at some other time with a delay, and that probability distribution function both are same means what is the meaning is its statistical characteristics is independent of time. It means it is stationary process. So your mean and correlation and covariance function of your stationary random process, right? So stationary random process, it is independent of time. It will be same at all time. So mu x of t becomes mu x. That is, it is independent of t. It will be same if you observe the random process at any time. That is the meaning. And the autocorrelation function of x of t is, that is the correlation between the random variables x of t1 and x of t2. That is the correlation between the random variables observed from the random process at time t1 and t2, right? That is the expectation of x of t1 and t2. So expectation of x of t1 and t2 is given by this integration, and you can also take it as time instead of t1 and t2, you can take it as 0 and t2 minus t1. So t2 minus t1 is the difference in time, and the difference in time you are denoting it as tau. So Rx of tau, you can denote it as Rx of tau. So the Rx of tau, that is autocorrelation, completely depends upon your time tau. That is, what is the delay you are taking. It doesn't depend upon your what time or and all. It completely depends upon only the delay time, right? So that is one property of your autocorrelation function. And then auto covariance function is given as expectation of x of t minus mu x into x of t2 minus mu x, and that is given as autocorrelation minus mu x square. And if you're having this two property is satisfied, that is mean is constant, and then the autocorrelation function completely depends upon the time tau, then that process we are calling it as a wide sense stationary random process, right? That is the mean is constant, it does not depend upon time, and the autocorrelation function depends only upon the time difference, right? So if these two points are satisfied, it means it is a wide sense stationary. So if it is a wide sense stationary random process, it need not be stationary, that is strict sense. Triple essential strict sense, and wide sense means it is WSS. So if a random process is strictly stationary, then it means it will be also wide sense stationary if the first and the second order moments exist, right? So if the first and second order moments exist means then it means it is If it is a triple S, it will be compulsory white sense. But a white sense will not be also a strictly stationary process. And this is the graph showing your autocorrelation function with tau. So for slowly fluctuating random process, how the autocorrelation changes, and for rapidly fluctuating random process, how the autocorrelation changes. It is given. So what is the inference you are getting from this autocorrelation graph is it gives about the dependence of the random variables obtained from taking the random process. All right. So for slowly fluctuating random process, it is that correlation is getting taking some time to go to zero. For rapidly fluctuating, it is becoming uncorrelated at a short span of time. So that's what I have explained here. So if it is two different random processes, x of t and y of t, then it is called as cross correlation. That is or xy of tau. It is cross correlation. Autocorrelation, you are denoting it as or xx or x or x of tau, right? And cross correlation, you are denoting it as or xy. That is a correlation between x of t and y of t. So it is expectation of x of t plus tau and y of t. So unlike your autocorrelation, this autocorrelation, if you see Rx of tau, it is a even function. That is, it is symmetric about zero. But your cross correlation may not be like that. But however, it will also satisfy this condition: x y of tau is equal to or yx of minus tau. The power spectral density you will be seeing in the next slides. So I will tell during that time. So what are the properties of autocorrelation? So your autocorrelation is defined as expectation of x of t minus tau and x of t. And if you put tau is equal to 0, it becomes expectation of x square of t. That is the mean square value of a random process. So the autocorrelation value at tau is equal to 0 is expectation of x square of t. So expectation of x square of t is nothing but your average power of the signal. So the value at tau is equal to 0 is the average power of that random process, and it is obeying the even symmetric conditions. Rx of tau is equal to Rx of minus tau, and the Rx of tau value, magnitude value, will be always less than or equal to Rx of 0. That is a maximum value. If you see this graph, the maximum value occurs at tau is equal to 0, and all other values will be less than the value at tau is equal to 0. That is one property of the autocorrelations. So let's see one example. So participants, if you are having any doubt, you can interrupt me and ask me questions. Okay. So I will continue. So you are having an example of a sinusoidal wave with random phase, right? X of t is given as a cos omega ct plus theta, and where your phase, you can call it as phi or theta anyway. So it is uniformly distributed from 0 to 2 pi. So uniform distribution means it is given as f theta of theta is equal to 1 by 2 pi. Theta lies in 0 to 2 pi. This is your equation for the uniform distribution. That is 1 by b minus a. So 0 to 2 pi minus 0, it is 1 by 2 pi. So the mean, you are finding the mean of the random process. So mean is given as expectation of x of t. So you are integrating from 0 to 2 pi. X into fx of x dx is your formula. So expectation kandupidikana x of t multiplied with the distribution and integrated. Excuse me. 1 minute. Sorry. So coming to this, you are having x of t with the distribution. So distribution of x of t, this a is constant, fc is constant, and only this theta is varying. So it is given as theta is uniformly distributed in the interval 0 to 2 pi. So you are writing the uniform distribution formula. It is 1 by 2 pi. That is 1 by b minus a is your formula. So 1 by 2 pi, theta lies between 0 and 2 pi. So this autocorrelation function depends upon the time difference அப்படின்னு சொல்லி prove பண்ண போறோம். So you are taking your autocorrelation as expectation of x of t and x of t plus tau. So x of t, you write the ca cos omega ct plus theta, and x of t plus tau, you are writing instead of t, you are substituting t plus tau. So you are getting omega ct, omega c tau plus theta. All right. So this a into a, you are taking it as a square. So you take this a square out. This you can use the formula. Usually all this cos a cos b formulas will be used mostly. So cos a cos b, it is cos a plus b and cos a minus b. Right. So this is a plus b, means you are adding this and this. So you are getting 2 omega ct, that is here 1 omega ct 2 omega ct plus omega c tau plus theta. And if a minus b means this omega ct theta and omega ct theta will get cancelled, and you will have omega c tau. So it is omega c tau. So you are, and if this is the multiplication cos into cos, you are making this as addition. One is a plus beta and another one is a minus beta. So you are separating the expectation of this a plus beta, and another one is the expectation of a minus beta, right? So if you find the expectation of this, that is, you have to integrate it from 0 to 2 pi, a cos 2 omega ct plus omega theta plus 2 theta, 1 by 2 pi 2 d theta. So yeah, this is nothing but the same thing we have done here, right? So if you integrate this, what will you get is, if you take this as cos omega ct plus theta as cos a cos b minus sin a sin b, right? So cos omega ct you can take out, which is a constant. Only your cos theta you are going to integrate. So you split this using cos a cos b formula. So cos omega ct you will take out, and you will have cos theta inside the integration. So cos theta, if you integrate, you will get sin theta. And sin theta, putting the limit 0 to 2 pi, you will get it as 0 value. Similarly, the next term also you will get the 0 value. And so this total value will be 0. Right? So the integral of this value will be 0. So here also this integral value will be 0. And so you will get only this value, a square by 2 cos omega theta. So only this value will be the answer for this autocorrelation function. So autocorrelation function is given by a square by 2 cos omega ct, omega c tau. So if you see a sinusoidal signal with a random phase, x of t is taken, and your that autocorrelation function is another sinusoidal signal, only with variable t changed as tau, and with amplitude a square by 2. It is of amplitude a, the random process, and it is changed. If you find the autocorrelation, it is also a sinusoidal signal with amplitude a square by 2, and with time is changed to this delay time, that is tau. So the problems, if you want to change these problems, it will be asked that sometimes the frequency is fixed, right? Your omega c is fixed, and your amplitude is a random variable, and the amplitude is changing. So you have to take that omega ct, or that it will not be specified anything about theta, right? So you have to take into account the expectation of a, and your cos omega ct term will be remain as a constant value. So according to the problem, you have to calculate out which is a random variable there. Sometimes it will be given a as a random variable, or here if it is given theta as a random, which is distributed uniform distribution 0 to 2 pi. Right? This is one important basic thing of finding your autocorrelation of a sinusoidal signal with random phase. Suppose you take a two process, one is cos 2 pi fct plus theta, and another one is sin 2 pi fct plus theta, and it is a modulated process, that is multiplied with x of t, right? X of t multiplied with cos. This is nothing but if you take this is your message signal, x of t unnode message in message multiplied with your carrier frequency, it is nothing but your double sideband signal, right? This is a modulated signal. So this is one modulated signal x1, and x2 is a modulated signal with x sine, right? One is modulated with cos and another one is modulated with sine. And if you find the autocorrelation of this process, that is correlation between x1 and x2. Okay, it is actually the cross correlation, right? So the correlation between x1 and x2 is expectation of x1 of t and x2 of t minus tau, right? So if you substitute this x of t cos 2 pi ct and x2 of t பதில் இங்க t minus tau, இங்க t minus tau போடுவோம். So you will get this value. So this x of t and x of t minus function we are taking. So this x of t minus tau, this is nothing but an autocorrelation function. So it is given as 1 by 2 or x of tau, right? And this value expectation of sine into cos term, all right? So the previous you have to have cos into cos term, right? This is you are having cos into cos. So you are writing it as cos a plus b, cos a minus b. And here you are having sine into cos. So it is sine a plus b plus sine a minus b. So a plus b, you should be conscious in this. That is sine term is a and cos term is b. Okay. So you are having this. So having this as a 2 pi fct minus 2 pi fct tau plus theta, this total value is a and this value is b, right? So sin a minus b, sin a plus b potana, you will get this two terms. And if you integrated this as previously told, that is you will be integrating this with respect to or distribution of theta, that is 1 by 2 pi d theta, then the value will be 0. That is done here, right? This is integrating this expectation of this. You have to integrate it from 0 to 2 pi with the distribution 1 by 2 pi d theta, and this value will become 0, right? The same thing here, this value will become 0 and you will get 1 like this value, that is minus. So you are having minus 1 by 2 rx of tau sin 2 pi fc tau as an answer for the autocorrelation function of the quadrature modulator process. So if you put tau is equal to 0, then sin 2 pi fc tau will become 0. So at tau is equal to 0, the autocorrelation is 0, which means your process, that is x1 of t and x2 of t, are orthogonal to each other. From this equation itself, you can tell that it is cos and sine, so it implies they are orthogonal, right? So here you have proved that autocorrelation is 0 at tau is equal to 0, and so it is x1 of t and x2 of t are orthogonal. So now next, so you have studied about the autocorrelation function of a random process, which is the most important thing. The problems will be asked only in this. That is, given any signal or any random process x of t, it will be asked to find the autocorrelation. So just you have to find the expectation of x of t plus tau. Right? That is the method for finding the autocorrelation of a random process. But you should clearly understood whether it is given theta as a variable or a as a variable, right? So you clearly go through the problems, which is given as a random variable. So this is a modulator process. Next time we will see about an ergodic process. So if you take x of t as a Weissenstein stationary random process with mean mu x and autocorrelation rx of tau, right? And your small x of t is your realization, means it is a sample function of the random process. So we can take the time average. Usually if you take the mean and the correlation, what we have seen is that is the mean. What you have seen, this is mean of the random process is expectation of x of t, x into fx dx. This is nothing but an ensemble average, right? And autocorrelation is also expectation of x of t1, x of t2, that is given as rx of tau, denoted as rx of tau. That is also an called as an ensemble average. So if you, that is another average called as a time average. So the time average is 1 by 2t in the interval minus t to 2t x of t dt. That is you are going along the process. Yes, ma'am.
Ma'am, a little bit slow will appreciated, ma'am, because we feel little slow, ma'am.
Okay, okay.
Okay. Okay.
Okay, ma'am. I thought I'm going very slowly. Okay.
Okay, ma'am.
Okay, I'll
Okay.
tell little bit slow.
Okay.
Should I repeat that problems? Students, you can take.
Indu ma'am, you can. Ma'am is asking whether the speed of the students. What do you feel?
Students, ma'am, you can continue, ma'am.
Okay, okay. Okay, anything you want
recording
to
process.
repeat? Anything you want to repeat it, you can stop me, okay?
Okay, ma'am. Okay,
Okay,
ma'am.
okay.
Okay.
Thank you,
So
ma'am.
you are, okay. Now you are going to see about ergodic process. So what we have seen up to now, that is called as an ensemble average. Another one you are having as a time average. All right, that is the statistical average. You are calling it as an ensemble average. You find the mean and autocorrelation so far that denotes the ensemble averages. And if you time average means you are going along the process, right? Ensemble average, you are going across the process. You are going along the process. That is, you are integrating x of t from minus t to t, taking some observation interval from minus t to t. You are integrating it and 1 by 2t. And if t tends to infinity, then this time average, when it approaches your ensemble average, then it is means it is ergodic, that process is ergodic in the mean. That is a mean. Now that is your time average approaches your ensemble average as t tends to infinity. Then the process is said to be ergodic in the mean. Similarly, if your autocorrelation average, you are having the time average autocorrelation function. The formula is 1 by 2t minus t to t integral x of t plus tau x of t dt. So this is called as a time average. So if this time average becomes equal to the ensemble average, that is Rx of tau, as t tends to infinity, then the process is said to be ergodic in the autocorrelation function, right? So the process x of t, a random process, you are having a x of t, random process, you can find the statistical averages, that is your mean of the random process and the autocorrelation function of the random process. Similarly, you can find the time average of the random process, that is the mean of the random process and the autocorrelation, time average autocorrelation function. And if this both are same, that is time average function is equal to the ensemble average, then the ergodic process is said to be, the random process is said to be ergodic in the mean and ergodic in the autocorrelation function. I hope you understood this. So for a process, ergodic process to be for a random process to be ergodic, it should be Whitesand stationary. That is a necessary condition. If it is not Whitesand stationary, it cannot be a ergodic process. Next, an important process is a Gaussian process. So for the Gaussian process, you are taking observing random process at time t1, t2 up to Tn for all n, and you are taking the random variables x of Ti, and they are jointly having the Gaussian density function, then that process is Gaussian process. That is, if you take a Gaussian process and you are observing that a Gaussian process at various time intervals C1, T2 up to Tn, the joint distribution of that random variables will be jointly Gaussian. Then that process, you are calling it as a Gaussian process. So the Gaussian process can be specified completely by mean and the autocorrelation function. If you want to describe a Gaussian process, it is enough if you know the mean and the correlation, that is mean and the variance. If you know, you can completely define the Gaussian process. So a Gaussian process is obeying the two conditions, that is mean is constant and the correlation depends only upon the tau. So it is a Whitesand stationary random process. And since the process is defined completely by this only this two things, complete statistical description, Gaussian process will be a strict sense stationary process also, right? And many, you are having many properties of Gaussian process. That is, when Gaussian process pass through your LTA system, the output will be also Gaussian like that. So you have, so far you have seen about what is a stationary process, you should know, and what is a Whitesand stationary process, and what is an ergodic process, and then what is a Gaussian process, right? Next, we'll go to the topic, that is transmission of a random process through a linear time invariant filter system. All right, if you pass a random process through a LTA system, you are getting the output and you're going to find that. So before that, you should know what is meant by linear and time invariant system, right? So that system, any system, we denote it as L. The system, it is a linear system if it obeys these conditions. That is A1 x of t1, A2 x of t2. It will be A1 into L x of t1 plus A2 into L of x of t2. That is output of the random process is L of x of t. That is L represents a system. So the x of t pass through a system and you are getting output as y of t, right? So you are passing x of t1 plus x of t2, then the output will be y of t1 plus y of t2. That is an image. And the constant a1, you can multiply it, a1 and a2, a1 and a2 are separated. Then it means it is a linear system. And similarly, time invariant system, if you are passing x of t and you are getting the output as y of t, and if you are passing x of t minus t naught as an input, the output will be y of t minus t naught. That is the shift in the input results in the same shift in the output also, right? So it is time invariant system. That is the system. It is if you are passing a random process x of t and observing at some time, and at some other time, if you see that the output x of t minus t naught, if you pass, it will be y of t minus t naught. So the shift in the input results in the same shift in the output. That is a time invariant system. All right. So what is a linear? What is a time invariant? You should be clear. So usually you'll be dealing with this LTA systems, linear time invariant systems, and you have to specify any system. It can be a filter or like that by using an impulse response. So what is an impulse response means? The response of the system to an impulse. Right? You are having giving dou of t as an impulse. In signals, you would have studied about that impulse. Dou of t. So dou of t, when you're given to a LTI system, the output is called as an impulse response of the system, which is denoted as h of t, right? So the response of the system to the impulse, you are calling it as a impulse response. So now coming to this, you are passing a random process x of t through a linear time invariant system, which is having the impulse response h of t, and output you are getting as y of t. Right? So the output y of t, it will be given as the convolution of x of t and h of t, which you would have already studied, right? The output y of t is equal to convolution of x of t and h of t. If it is in frequency domain, means y of f, it will be convolution in time domain. It will be converted to multiplication in frequency domain. That is x of f into h of f. You will get it as y of f. Right? So now you are not going to about the frequency domain. Just I'm telling that. So your y of t is convolution of x of t and h of t. What you are going to find is you are going to, this is a random process with mean and autocorrelation function. Mean is given as mu x and autocorrelation is given as rx of tau. And you are going to find what is the mean of the output random process and what is the autocorrelation function of the output random process and what is the cross correlation between x and y, right? You are giving some input signal to a system and you are getting an output signal. So you know the statistical characteristics of this input. So you are going to find the statistical characteristics of the output, right? That is this derivation. So y of t is convolution of x of t and h of t. So this convolution formula you have written as h of tau 1, x of t minus tau 1. Or it can be also written as x of tau 1 and h of t minus tau 1. Both are same, right? D tau 1 integration is from minus infinity to plus infinity. This is the convolution formula. Okay, yeah. So h of t is an impulse response. Now you are going to find the mean of y of t. So to find the mean of y of t, you have to find the expectation of y of t, right? So the expectation of y of t. So expectation of this integral, you are substituting the y of t here. That is h of tau 1, x of t minus tau 1 dt1 integration. So this total part is your y of t, right? So you're going to find the expectation of this, right? So since your system is stable, you can interchange your this integration and your expectation, right? And so you are bringing the integration as out and you are moving the expectation inside, right? So moving the expectation inside, since this X is your random process, this H of T1 is an impulse response. You are taking this out and you are putting as expectation of X of T minus tau1 d tau1, right? Hope you understand this. You are interchanging your integration and the expectation, and H is nothing but impulse response of the system which will not change. And so only this X of T minus T1 is your random process, right? So you are putting as expectation of this X. So expectation of X of T minus T1 is mu X of T minus T1 d tau1, right? So this mu X of T minus tau1, you can denote it as mu X of mu X itself, since you are telling that this random process is a stationary random process. That is, if the mean is constant and it does not depend upon time. Already you have seen, if it is a stationary random process, then your mu, then your mean is constant. That is independent of time. So mu X T minus T1 is nothing but mu X. So you take mu X as outside. So the mean of the output random process mu Y is given as the mean of the input random process mu of X into integration H of tau1 d tau1. So if you take this H of tau1 d tau1 integration, this is nothing but the frequency response H of F. That is, if you want to find H of F, which is a frequency transform, how will you write? It is integration. I want to find the frequency transform of the impulse response H of t. So H of F is equal to H of t exponential minus j2 pi f t dt. And if f is equal to 0 means if your exponential term equals 0 term will be 1. So you will get only this H of t dt, right? So this is nothing but the frequency response of the system at f is equal to 0. So it is written like this, or you can have this equation as such. So the mean of the output random process is given as the mean of the input random process multiplied with the frequency response of the system at f is equal to 0. That's what we have proved here. Next, you are going to find the correlation between x and y, right? X is your random process input and y is your random process output. So correlation between x and y, you are going to find the expectation of x of t1 and y of t2. So x of t1, you have written as such, and y of t2, you are using the convolution formula. That is, y of t is x of tau, h of t minus tau d tau. So instead of tau, you are using some other variable s, right? And time is instead of t, you are having t2. So this is t2. So you are putting t2 minus s ds. Instead of tau, you are using s as a variable to avoid confusion. Yeah. So x of t1 நம்ம அப்படியே வச்சுக்கிறோம். This x of t1 you are keeping like this. And the y மாத்திரம் நம்ம எப்படி எழுதுறோம்னா convolution of x and h. Right? Convolution of x and h, it is y. So you are substituting this. Then again interchanging your integration and the expectation, right? You bring the expectation operation inside and this integration is coming out. Okay, so it is expectation of x of t1, x of s, and h of t2 minus s ts. So this is nothing but the expectation of x of t1, x of s. It is autocorrelation, all right? Autocorrelation between the random process taken at time t1 and taken at time s. So it is rx of t1 minus s. Rx of tau that is t1 minus x, and this h of t2 minus s ds. Here you are using one substitution, that is this t2 minus s or s minus t2, you take it as u, right? S minus t2, you are taking it as u. So it will get that h of, sorry. So s minus t2, you are taking it as u. So t2 minus s, it will be minus u, right? And here you substitute s is equal to u plus t2. Right? The substitution use பண்றோம். U is equal to s minus t2. So your s is equal to u plus t2. So u plus t2 substitute பண்ணனா you will get the next step. T1 minus t2 h of minus u du. Right? So T1 minus T2 is nothing but the delay time, that is tau. So Rx of tau minus u into h of minus u du. So integration of Rx of tau minus u into h of minus u du is nothing but a convolution formula. So it is a convolution between Rx of tau and h of minus tau. Right. So what you have derived is, we have derived that the autocorrelation function, cross correlation function of your input and output random process or xy of tau is equal to Rx of tau convolution h of minus tau. So similarly, if you go the autocorrelation of the output random process, in the same way, here you are substituting y of t to அப்படியே வச்சுட்டு y of t1 split பண்றோம் using the convolution formula, and then using the substitution u is equal to s minus t2, you will get it as it is the convolution of or xy of tau and h of tau. Okay, yeah. The same way, இங்க வந்து நம்ம x of t1 வச்சுட்டு y of t2 வந்து பிரிச்சிருக்கோம். இங்க வந்து you are keeping your y of t2 and y of t1 பிரிச்சு எழுதிருக்கீங்க, and using the same substitution u is s minus t2 substitute பண்ணுவோம். Substitute பண்ணி finally this is nothing but the convolution formula. This is nothing but the convolution formula. T1 minus T2, you put it as tau. So, tau minus u du or xy of u, tau minus u du. So, this is a convolution or xy tau into h of tau. So, the output random process autocorrelation is given as the convolution of Rx of tau, h of minus tau and h of tau. That's what you have derived. This is also this is one derivation, this is another derivation which you can go through it. Same thing, right? Since it is time up, I think I will just tell the final thing. That is your mean of the output random process is the mean of the input random process multiplied with the integral of h of t dt, and your cross correlation between my input random process and output random process is the convolution of input random process and h of minus tau, and the correlation of your output random process is the convolution of the input random process with h of tau and h of minus tau. Next, we'll go to about the power spectral density. That is the power spectral density. That is, it is a function. This is also a most important tool in studying your random process or in communication systems. So the power spectral density, it will gives the distribution of power of a random process. So if you take a deterministic signal, you will see that in order to see the signal, whatever the frequency content, you'll be going for Fourier transforms, right? Similarly, here the power spectral density, it is gives a distribution of power for a random process with frequency. Okay, so how you are finding the power spectral density is nothing but it is the Fourier transform of your autocorrelation function. So your power spectral density is given as anything you wanted it? Ma'am?
You
Yes,
can
ma'am.
proceed. You can proceed,
Okay.
ma'am.
Okay. So the power spectral density is the Fourier transform of our autocorrelation function is x of f. The power spectral density is given as capital A S suffix x of f is minus infinity to plus infinity, or x of tau exponential minus e2 pi f tau d tau. That is a Fourier transform of your autocorrelation function, right? So this is the two equations. If you want our autocorrelation function from the power spectral density, it is inverse Fourier transform. And if you put tau is equal to 0 at the second equation, if you put tau is equal to 0, then it means if you this value will become 0. And so if you integrate your power spectral density curve, you will get the value at tau is equal to 0. Okay. So this equation we are calling it as a Vienna-Kinchel relations. These are all the properties of the power spectral density. Similar to your autocorrelation, power spectral density is even, and then the area under the power spectral density curve, it gives autocorrelation function, or it gives the average power, right? This is an important information you got from the power spectral density. That is, if you integrate the power spectral density curve in the limit minus infinity to plus infinity, you can find the average power. That is, you can find the value of autocorrelation at tau is equal to 0. which is nothing but the average power of the signal. So if the output power spectral density is given as is y of f is equal to h of f magnitude whole square into input power spectral density, right? If you take the Fourier transform, நம்ம எப்படி சொல்லுவோம் y of f is equal to x of f into h of f. But if it is power spectral density, then s y of f is equal to h of f magnitude whole square into is x of f. So take an example, you're having a sinusoidal wave with random phase. Already you have seen this. So you have derived your autocorrelation as a squared by 2 cos 2 pi f c tau. And if you want to find the power spectral density, you have to find the Fourier transform of your a squared by 2 cos 2 pi f c theta. So Fourier transform of this, you will get your sx of f. Okay, so in the Fourier transform equation, so Fourier transform directly you can find, that is your cos 2 pi fc tau or t, whatever it may be. So it is Fourier transform is nothing but the delta functions at f minus fc plus delta function at f plus fc. Okay, so you can directly put a square. Again, you will have 1 by 2 term here. So Fourier transform of this is 1 by 2 delta function f minus fc delta function f plus fc. So your answer will be, already you are having a square by 2. So a square by 4 delta function f minus fc plus delta function f plus fc. Okay, yeah. So this is your power spectral density of your random sinus of a sinusoidal wave with random phase. And if you plot the power spectral density, it is a square by 4, a delta function at fc and a delta function at minus fc. So this is f minus fc shifting right and f plus fc is shifting left. So consider you are mixing a random process with a sinusoidal process. That is, you take x of t as a random process, cos 2 pi fc t plus theta, it is a sinusoidal process, and your theta is uniformly distributed from 0 to 2 pi, and you are going to find the autocorrelation of output. So you are having a random process with the sinusoidal process, and you are finding the autocorrelation of the output random process, that is y of tau. Right? So substituting this, again same way, you put y of t plus tau. Right? Y of t plus tau substitute panela. 1 minute, my mouse pointer is not working. Okay. So are you able to see my pointer?
Yes, madam. The
Okay.
pointer is
Ma'am,
moving.
yes, ma'am.
Okay. So expectation of y of t plus tau. All right. So y of t அப்படியே எழுதிக்கிறோம், x of t cos 2 pi fc t plus theta எழுதிக்கிறோம். y of t plus tauங்கிறது x of t plus tau cos 2 pi fc t plus tau plus theta. So you will get it as cos 2 pi fc t 2 pi fc tau plus theta. All right. So this cos terms I have separated, and this x of t terms you have separated. So it is expectation of x of t plus tau, x of t is nothing but autocorrelation function Rx of tau. And here you are having the expectation of multiplication of two terms cos, right? So this already you have seen. This will be cos A cos B. So you will split it as cos A plus B plus cos A minus B. And you will get the term 1 by 2, right? So one is a plus beta and another one is a minus beta.
Indu ma'am. Ma'am has gone offline. Call her. Ma'am. Shanti ma'am, are you there?
Ma'am, she's here only, ma'am.
Offline.
Offline. It
No, it
shows
shows
offline,
offline.
ma'am. I'll call her. I'll call her.
Okay.
Call பண்ணுறேன் மேம்.
Students, just wait. She will join back. Students would like to post your query. Okay, don't if you are afraid of posting a query in chat box means you can enable your mic and ask. Okay, not comfortable with English means you can ask your queries in Tamil also. Don't worry because it is a doubt clearing session only. We want all the students to get benefited. That is the intention of this webinar.
Ma'am, she is joining, ma'am.
Okay, ma'am. Okay.
Ma'am, now you can share your screen, ma'am.
Yes, ma'am. Wait, I'll try to share the screen. Then how I come out? Slide is visible, ma'am?
Yes, ma'am.
A minute. So we are talking about past spectral density. So I think this one is looking at it. That is a mixing of random process with the sinusoidal process, and you are finding what will be your correlation, autocorrelation. All right. So substituting again following the same procedure, expectation of x of t plus tau and x of t will get it as rx of tau, and then expectation of the cos into cos term will get it as cos a plus b term and cos a minus b term. And this a plus b term, if we integrate it with the distribution 1 by 2 pi d theta, this term will become 0, which is derived in the previous problems. And you will get only the cos 2 pi fc tau terms. Okay, yeah. So your answer will be 1 by 2 rx of tau cos 2 pi fc tau. That is your autocorrelation, which I think you already did. Then what is the pass vector density? You have to find your Fourier transform of your autocorrelation functions. So the Fourier transform of autocorrelation function R y of tau, you have to find the Fourier transform of this Rx tau into cos 2 pi fct. Okay, yeah. So if you are having only cos 2 pi fct and a constant term, the previous slide, what you have seen, see this is your cos 2 pi fct and one constant term a square by 2. So you can put it as a square by 2 into 1 by 2 delta function f minus fc plus delta function f plus fc. So x square by 4 you are getting. So here you are having a multiplication of a Rx of tau and cos 2 pi fct terms. Rx of tau and cos 2 pi fct term. This is nothing but similar to a modulated signal. You will have a message into cos, right? So if you are multiplying a time function with a cos function, then the resulting Fourier transform will be the shifted version of your message, Fourier transform of your message shifted at a minus fc and plus fc. Okay, so you can directly put your R y of tau as 1 by 4 and Rx of tau order Fourier transform will be Sx of f. So 1 by 4 Sx of f minus fc plus Sx of f plus fc. That is your pass spectral density of the random process y of t. So yeah, so what you're doing is you're finding the autocorrelation and then finding the Fourier transform to find the pass spectral density. Because why you're going for pass spectral density, which will be very excuse, which will be very much useful in your analyzing your communication system easily. In deterministic signal, we'll be going for a frequency domain. Similarly, yes, solving will be easy. So pass spectral density is nothing but Fourier transform of your autocorrelation function. Autocorrelation எப்போ போல கண்டுபிடிச்சிட்டு அதுக்கு Fourier transform கண்டுபிடிச்சோம்னா that will give you SY of f. So this is another example problem. So here we are given x of t as 3 cos omega t plus theta and y of t as 2 cos omega t plus theta minus pi by 2. So you have to prove that Rxy of tau, not Xx of tau, Rxy of tau is less than or equal to Rxx of 0 or Yy of 0, right? So you are finding your autocorrelation already have derived. That is, if it is an a cos omega t plus theta, the autocorrelation will be a squared by 2 cos omega tau, right? So they already derived பண்ணிருக்கோம். So here you have derived that this autocorrelation is a squared by 2 cos 2 pi fc tau, right? So same thing, you can directly use the formula. So a squared by 2, 3 squared by 2 cos omega tau, right? Tau is equal to 0, the value will be 9 by 2. Similarly, R y of tau, it is 2 cos omega t plus theta minus pi by 2. So it is 4 squared by 2. So it is, 2 squared by 2. So it is 4 by 2, 2. So 9 by 2 into 2 square root, we are getting the value as 3. Now next step is you have to find the correlation between x and y. So you are finding x of t into z of t minus tau. X of t, z of t minus tau. So you're substituting x of t here and sorry, x of t and y of t minus tau. So you are substituting x of t here and y of t minus tau. And same method, cos into cos, we are using cos a plus b and cos a minus b formula. And that cos a plus b term, it will become 0. And you're having the cos a minus b term as cos omega t plus omega tau plus pi by 2. So 3 cos omega tau plus pi by 2 is your correlation between x and y. And magnitude of that will be 3. So already you have seen that multiplication of that Rx of 0 R by y of 0 square root is 3. So what you infer is your autocorrelation of tau is less than or equal to autocorrelation of xx at 0 and autocorrelation of yy at 0. So this is also an example of another formula. You are given w of t and z of t, and it is asked to find the correlation between w and z. Should I explain this? We'll go to next topics. This is an example of a process passing through a LTI system with the filter transfer function as h of t is 1 by pi t. 1 by pi t because it is nothing but a Hilbert transform, right? So you are giving a Hilbert transform as a system, and it is asked to find the output y of t correlation and the cross correlation between x and y. So you're directly using the formula. The mean into h of t dt, h of t to 1 by pi t power. And next one is xy of tau. So xy of tau is Rx of tau convolution of h of minus tau. So h of minus tau you are putting as 1 by minus pi t, right? So this is nothing but formula for Hilbert transform of a signal, right? The Hilbert transform of a signal is convolution with 1 by pi theta. It is minus Rx cap, that is a Hilbert transform, minus Rx cap of tau to become. And Ry of tau, you are having the formula here. So you are using only this formulas. That is, you are using this formulas. Rxy of tau is equal to Rx of tau convolution h of minus tau. And Ry of tau is equal to Rx of tau convolution h of tau and convolution h of minus tau. Right? Or Ry of tau is convolution of Rxy of tau into h of tau. So that is we are using and solving this in the ECE method. So Ry is equal to Rxy convolution h of tau. So Rxy you have already find it as a Hilbert transform. So if you find the Hilbert transform and again you are finding the Hilbert transform, you will get your minus of Rx of tau. So minus of Rx of tau, minus minus, it will get cancelled and you are getting Rx of tau as answer. This is an example. This example also you go through, since it is independent random variables, then it will be that a correlation between A and B will be 0. That thing will be used here. Since it is independent, A of t and B of t are independent, and it is given also 0 mean. That is expectation of A of t and expectation of B of t is 0. So independent means here it is expectation of A and expectation of B. Expectation of not independent means expectation of AB is equal to expectation of A into expectation of B. And since expectation of A is 0, we are getting the product as 0. And so we are finding the correlation between W and Z. So in that RAB and RBF tau would be 0. RAA and RBB it is given. Substitute that and find the output. So that's all about your random process unit. So in this unit, you have to study main concept about random process, what is a stationary process, and what is a wide sense stationary, what is a ergodic process, and then the most important process usually used in communication systems, Gaussian process. And why you are using the Gaussian processes? If you take any physical phenomena, it can be, it is found that it can be described by means of Gaussian random variables. It is Gaussian distribution. It is converging to the Gaussian distribution. It is verified, and also it is mathematically easy. So you are mainly using the Gaussian process in communication systems. And you have to study about the properties of that Gaussian process. Then you are having that transmission of a process through your filter. If you transmit a random process through a filter, what will be the output random process characteristics? What will be the mean? What will be the autocorrelation? Or what will be the power spectral density like that? So the maximum probability is of asking problems in this unit. So problems will be what we have discussed now. Similar to that, random process will be given and asked to find the autocorrelation, or asked to find the power spectral density, or asked to find whether the process is wide and stationary, or whether the process is ergodic, right? So problems will be like that. Or you are passing some random process through a filter, and the filter will be, maybe it will be a or it can be a differentiator, or like that. So what will be the output? What is the output mass spectral density? So like that choice the problems will be asked. So if you go through all these problems one by one, and if you work it out, and if you very well understand the concepts, right, then you can easily possible to work out the problem, even if it is some asked with some twist, right? So I think I can go to the next one about noise. Ma'am, shall I discuss about noise, ma'am?
Yeah, ma'am.
Okay.
Students, ma'am can continue, right?
Because it
Continue,
is,
ma'am.
okay.
Yes, ma'am. Yes, ma'am.
Okay. So I'll go through noise for a half an hour, quickly, right?
Okay, ma'am. Take your time.
Okay. So noise is an unwanted signal that affects your received signal. It can be classified as many as a noise due to, that is, internal noise and external noise. All these things we have studied. For external noise, it may be due to atmospheric noise, galactic noise, or cosmic noise, right? Internal noise, you have studied about thermal noise, short noise, and all. So I'm straightly going to talk about your narrowband noise. So in order to know about a narrowband noise, you should know about white noise. So the white noise is nothing but it is having a pulse spectral density which is constant for all frequencies. Then that noise we are calling it as a white noise. That is pulse spectral density is n0 by 2 and it is constant for all frequencies. And that noise, white means it contains, white light contains all frequencies, equal amount of all frequencies. That's why you are calling this as a white noise. And pulse spectral density is W of F is given as n0 by 2 and your n0 is equal to KTE, where K is your Boltzmann constant and T is your noise equivalent temperature. And this is your pulse spectral density of white noise Sn of F. And if you find the inverse Fourier transform, you will find the autocorrelation. So the inverse Fourier transform of your constant value, you will get it as impulse, that is Rn of tau. So the autocorrelation function of your white noise is n0 by 2 rho of tau. So the noise, white noise means it doesn't mean it is a Gaussian. So if the noise is having a Gaussian distribution, then it is called as a white Gaussian noise. So in your communication, you will be maximum using this additive white Gaussian noise. So this is an example for white Gaussian noise. This is from taking a random process, an example of a random process, Brownian motion. Brownian motion, it is some particles moving on the water, random movement of particles on the water or on the surface. You can take it as a Brownian motion. That is one example. So this is a Gaussian noise, example of a Gaussian noise. This is an example how your signal plus noise added and what will be your correlation of Z, right? Signal plus noise added, what will be the correlation of Z? So it is given as a correlation of X plus correlation of noise. Since it is uncorrelated, X into N, it will become equal to 0, since it is uncorrelated, and also 0. So you are having your autocorrelation of Z is autocorrelation of X plus autocorrelation of noise, and pulse spectral density of Z is pulse spectral density of X plus pulse spectral density of noise. So if you take a white noise, the white noise, when it passes through a low pass filter, right? White noise is having equal pulse spectral density like this straight line, it is n0 by 2. When it is passed through a low pass filter, you are getting the pulse spectral density curve like this. That is n0 by 2 lies between, if the low pass filter is having the bandwidth B, it is minus B to B. So this is your pulse spectral density of a filtered white noise, that is low pass filtered white noise, right? So if you see the inverse Fourier transform of your Sn of F, you will get the autocorrelation functions. So the rectangular function, if you want to find the inverse Fourier transform, then it will be your sinc function. Directly you can draw the sinc function as your autocorrelation function. So Sn of F is n0 by 2 for frequency minus B to B, and your autocorrelation function will be n0 B sinc to beta, right? So that is you are transforming your rectangular function to your sinc function. sync function will cross 0 at 1 by 2b, 2 by 2b, 3 by 2b, like that. Right. So we have studied what is a white noise. That is white noise having power spectral density same at all frequencies. When it passes through a low pass filter, you are getting Sn of f like this. And when you pass it through a band pass filter of center frequency Fc and bandwidth 2b. So Fc then Fc plus b, Fc minus b. This will be the modulation of a modulated signal, usually a AM signal or PSPAC signal. It lies in the frequency Fc, Fc plus b and Fc to Fc minus b. So this is a band pass filter white noise. Power spectral density of band pass filter white noise, yes, suffix n of here. And this noise we are calling it as a narrow band noise. So any communication system, if you see your modulated signal added with noise, and first initial stage will be a band pass filter, and the filter bandwidth will be such that it allows the modulated signal. So the filter will allow a noise in that modulated signal bandwidth, right? So if you take S of t plus n of t, not noise is not here n of t, it is w of t, that is white noise. So S of t plus w of t, it is given to the band pass filter, and the output is x of t. So x of t will be S of t plus n of t. So n of t is, you are calling it as a band pass filtered white noise, right? So that noise you are calling it as a narrowband noise, and this time domain diagram gives a sample function of your narrowband noise. And this Sn of your, it gives the power spectral density of your narrowband noise. This gives the power spectral density of your narrowband noise. So you can express the narrowband noise in terms of your in-phase and quadrature phase components. So for that, you are taking some part of a del f part. Suppose you take a del f part in this the frequency fk, and your noise you are representing it as ak cos 2 pi fkt plus theta of k, where ak is a random variable and fk is that particular frequency, and theta k is also uniformly distributed, and ak is a random amplitude. And so you are taking one slice, and in order to describe that noise n of t totally, you have to add it all things. So you're taking some slice and then adding. That is the summation k rise in the bandwidth, right? So summation nk of t. So it is summation ak cos 2 pi fkt plus theta k. And here you are using a one substitution as fk is equal to fk க்கு பதில் fk minus fc plus fc சேர்க்கணும். So fk minus fc plus fc சேர்க்கணும். இந்த இடத்துல cos a cos b ஃபார்முலா யூஸ் பண்ணலாம். So cos 2 pi fct term ஒன்று வரும். இன்னொன்று வந்து cos 2 pi fk minus fct term வரும். சரியா? So the cos 2 pi fct term வச்சுட்டு you are making your cos 2 pi fk minus fc ak plus theta of k as k and c. This is your in phase component, and this is your quadrature phase component, sine cos a cos b plus minus sin a sin b. Right? So this is your in phase component, and this is your quadrature phase component. So you're writing the narrowband noise as the in phase component into cos 2 pi fct minus your quadrature phase component into sin 2 pi fct, where your in phase component is given as summation k ak cos 2 pi fk minus fct theta k plus theta k, and your quadrature phase component is given as, right? Just you're taking a sample, a slice of a narrowband noise, and then you are deriving this equation. So if you're having your in phase and this quadrature phase, you can get your band noise, narrowband noise. That is, this is an in phase and quadrature phase. So in phase into cos minus quadrature phase into sin. Right? You will get your narrowband noise. And also, if you are having a narrowband noise, and if you multiply this n of t with cos and pass it through a low pass filter, you will get your in phase component. And if you multiply n of t with sine and pass it through a low pass filter, you will get your quadrature phase component. So you can extract in phase and quadrature phase from the band pass noise. And also, if you are given the in phase and quadrature phase component, you can also get your narrowband noise, right? So multiplying n of t with cos, if you see this, n of t is given as So this is your n of t cos in phase cos minus quadrature phase sine. So if you multiply with this cos term, you will have cos into cos term and sine into cos term, right? So cos into cos term, you can write it as cos a plus b plus cos a minus b. So cos a plus b term will be cos 4 pi fct and a minus b term will be 0. Similarly, sin a is cos b, sin a plus b, sin 4 pi fct term, sin a minus b 0. So if you pass it through a low pass filter, that 4 pi fct terms will be removed and you will get only the in phase component. Right? So that is multiplying n of t with pass and pass it through a low pass filter, you will get only the in phase component. 1 by 2 in phase வரும் அதுக்கு இந்த இடத்துல நம்ம 2 வச்சு மல்டிப்ளை பண்ணிடலாம். 2 வச்சு மல்டிப்ளை பண்ணலைன்னா you will get the output as ni of t by 2. Right? In phase component can denote it as ni of t and quadrature phase nq of t. If it is some case you can written it as nc and ns to denote it as cos and sine. Right? So these are some properties of your narrowband noise which you studied. And the power spectral density of your in phase component will be equal to the power spectral density of your quadrature phase component, and the power spectral density of in phase and quadrature phase component is given as Sn of f minus fc and Sn of f plus fc. This equation you will be mainly using in analyzing your noise performance of the systems. Right? So there are some other properties also. If it is Gaussian, then in phase and quadrature phase is also Gaussian. If n of t is 0 mean, nq of t also have 0 mean. If n of t is stationary, then ni and nq of t are stationary like that. Right? If n of t is Gaussian and it is power spectral density is symmetric, then ni and nq are statistically independent. Another method of this is one method, canonical form of representing your narrowband noise. Narrowband noise or இன்னொரு name தான் band pass noise. Both are same, narrowband or band pass. Right? Another method of representing a noise is using envelope and phase components. That is, you are writing n of t as r of t cos 2 pi fct plus psi of t, and this r of t is called as an envelope and psi of t is called as a phase. So r of t is given as the in phase component square plus quadrature phase component square root, and psi of t is tan inverse nq by ni. So this is your r of t, and this is your in phase component, and this is your quadrature phase component, and this is your psi of t. All right? This is your theta. This is your r of t, and theta is equal to 2 pi fct plus psi of t. Right? So both r of t and psi of t are sample functions of a low pass random process. And in order to see the distribution, you will have some derivation. That is, you will find the joint distribution of your ni and nq. So that ni is the in phase component and nq is the quadrature phase component. And the joint distribution of this in phase and quadrature phase. These are the random variables obtained by observing the random process of ni of t and nq of t. Right? It will be given as 1 by 2 pi sigma square exponential minus ni square plus n square by 2 sigma squares. And then you are substituting some thing like n1, ni is equal to r cos psi and nq is equal to r sin psi. So this is ni and this is in phase and quadrature phase. If you take ni in x-axis and nq in y-axis, r will be square hypotenuse. That is r cos psi will be ni and r sin psi will be nq. And using some substitution, you will get the joint distribution of r and psi. R is your envelope and psi is your phase. Right? The envelope of the noise and the psi is your phase of the noise. And if you find the distribution, it will be given like this. So if you see this equation, it is independent of psi. That is, it is independent of phase. So you can separate it. So 1 by 2 pi is the distribution of psi, and r by sigma square exponential minus r square by 2 sigma square will be your distribution of r. So the distribution of r is given like this: r by sigma square exponential minus r square by 2 sigma square. And if you substitute r by sigma square as phi, then you are having the distribution f of e is equal to p exponential minus v square by 2, which is nothing but the Rayleigh distribution formula. So what you infer from this is if a noise, you are having a the envelope of the noise, right? Where a phase of the noise is having uniform distribution and the envelope of the noise is having a Rayleigh distributions, right? It is having the maximum value at value v is equal to 1 and the value is about 0.6. Okay. So the Rayleigh distribution, you are having only the positive values because your envelope is having only the positive values. Your R of t is n I square t plus n q square t. Unlike your Gaussian distribution, Gaussian will have the negative value also, right? Mean 0 means it will do bell shape covering both the negative portion as well as positive portion. And this Rayleigh distribution is having only the positive values. So next one is you are going to see about the performance of noise. So the performance of noise, I'll go to another slide. In 1 minute.
Ma'am?
Wait 1 minute, I'll share the screen.
Okay.
Is it visible?
Yes, madam.
Yes, ma'am.
Okay. Slideshow is visible now?
Yes, madam. Yes, madam.
Yes.
Yes, ma'am.
So next you have studied about noise, and the main thing you have studied about noise is about white noise and about narrowband noise, right? Both are important noise in dealing with communication system. The white noise is mainly used, but actually it is not a practical realizable noise. You are modeling the noise using white noise, and then the noise filtered through a bandpass filter, then that noise we are calling it as a narrowband noise. So to analyze your noise in continuous wave modulation systems, we are modeling the noises, additive white and Gaussian noise. So you are transmitting a signal and you are receiving a signal, that if the received signal will get affected by noise. So in order to study the performance of a receiver, so you have to find your signal power and noise power, right? That is the main thing, how you are analyzing a performance of a system, whether it is an AM receiver or FM receiver or whatever it may be. So in an analog communication, if you want to study the performance, you have to study about the signal power and noise power, right? This is a receiver that is usual receiver. You have a RF stage and then mixer and IF stage and then demodulation stage. So you are simplifying that as you are having a modulated signal S of t added with noise, pass it through a band pass filter, and then that is the output. You are denoting it as X of t, and then your receiver, total receiver, you are modeling it as using a bandpass filter and a demodulator. Demodulator will be an important block in the receiver to get back the message from the modulated signal. Right? So same thing what I have told, it is given this. So your additive by Gaussian noise, it will have the pass spectral density A0 by 2. Okay. So this is your bandpass filter noise. After bandpass filter, the noise will be pass spectral density will be like this, and your BT is your transmission bandwidth. BT is your transmission bandwidth. It depends upon your modulation schemes. If it is your AM modulation schemes, then your BT will be 2W, and if it is an FM modulation, your BT will be given by cos source 2 into LF plus FM like that. So generally, you are written it as a transmission bandwidth BT. And your noise N of t can be represented using your in phase and quadrature phase component as Ni of t cos 2 pi fct and Nq of t sin 2 pi fct. So this is your x of t, is s of t plus n of t. And what is average noise power? Is average noise power, you have to integrate this pass spectral density curve, that is Sn of f. This integrate your pass spectral density Sn of f in this regions, right? So it will be n0 by 2 into 2 bt. So you will get it as n0 bt. Okay, so this is your average noise power at the demodulator input, right? So what you're going to do is you're having a receiver model. So you are going to analyze this receiver. What will be your signal power at this stage, that is the demodulator input, and what will be your noise power, and this is given as signal to noise ratio of the input, and what will be your message power, output you are getting your message, right? So here you are having a message. So what will be your message power and what will be your noise power at the output? So this will be the signal to noise ratio at the output. So this will be signal to noise ratio at the input, and this will be the signal to noise ratio at the output. That is one way you are going to derive it. Okay, yeah. So your input signal to noise ratio is average power of a modulated signal, S of t, and this is your x at the demodulated input. Okay, so average power of a modulated signal is and average power of noise, that is filtered noise, right? So that is SNRI, and average power of a demodulated message signal and average power of noise measured at the receiver output, then it is SNRO. And SNR channel, you are defining one definition, that is average power of a modulated signal by the average power of noise in the message bandwidth. That is, you are filtering the noise in the message bandwidth. Narrowband noise is the noise filtered in the modulated signal bandwidth, and if you are filtering a noise in the message bandwidth, then that is the average power of noise in the message bandwidth. That is similar to passing the message without modulation plus noise and pass it through a low pass filter. So that will be in the output, you will have a filtered noise in the message bandwidth. Okay, what is that average power of noise in the message bandwidth? That you are calling it as an SNRC, and that is to generalize for all modulation schemes. You are going for SNRC. So the figure of merit, it is given as SNRO and SNRC. That is the ratio of the output SNR and channel SNR. So when your figure of merit is value is more, means the performance of the system is good. Right. So this is the basic thing. The receiver or modeling like this, using signal plus noise, pass it through a filter, and then pass it through a demodulator. You are going to analyze the signal to noise ratio at the demodulator input and at the demodulator output. So that is your SNR in and SNR out, and figure of merit is SNRO divided by SNRC. So come to DSP-AC receiver. So we are going specifically, you are having a AM modulation and you are having a FM modulation, and so first we see about DSP-AC receiver. So you are having a DSP-AC modulated signal received added with noise and pass it through a band pass filter, that is X of t. So X of t is S of t plus W of t, pass it through a band pass filter, you will get it as N of t. So X is equal to S plus N, that is X of t. And what is a DSP-AC detector is, we are using a coherent detection. This all I have studied in the first unit itself. So it is again multiplied with a faster and then pass it through a low pass filter to get the message, right? So this is your coherent detector of your DSP-AC modulation. And this should be coherent. It means your local oscillator frequency and phase will be same as that of the frequency and phase used in your modulated signal, right? So it is passed to the FCT, and here you are omitting your amplitude. Okay, yeah. And so what you are going to do is you are going to analyze the signal to noise ratio at x of t, that is at this stage, and you are going to find the signal power and noise power at this stage. So you are writing the equation S of t CAC cos 2 pi FCT M of t, that is your base DC modulated signal, is nothing but your product of carrier and message, and you are taking your message power as P, that is pass total density of message, integrating from minus W to plus W. You are taking it as power of message as P, and so for this power of the modulated signal S of t is, it is nothing but the mixing of the process with the sinusoid. So the average power of your base DC modulator signal is, you're having here C as a constant you are including to make your noise and signal measure in the same unit. So this is maximum value. So you can power of this cos 2 pi FCT will be CAC divided by CAC square by 2, right? So C square AC square by 2, right? So this is the average power of your moderator signal S of t. So it is C square AC square by 2, and your message is P. You are multiplying your carrier with message. So C square AC square by 2 into P is your average power of your modulated signal. And then the average power of noise in the message bandwidth is WA0. Right? Average power of noise in the modulated signal will be A0 into BT. Right, so in the message bandwidth means it is N0 W, right? So how you are getting this is you are making this, already I told you, your noise filtered in your low pass filter, right? So this is your average power of noise in the demodulated input, right? That is N0 BT. So average power of noise in the message bandwidth is WNR. So SNRC, we are having C square AC square P by 2 as an average power of base AC modulated signal, and this WN0 is an average power of noise in the message bandwidth. So SNRC is ratio of this and this. So we are getting C square AC square P divided by 2 WN0. So now next you are going to find the message power and the noise power at the output of the receiver. So output of the receiver, you are passing it through a product modulator and then a low pass filter. Alright. So X of t is your S of t plus N of t. So you're writing S of t as CAC cos 2 pi FCT M of t, and N of t is NIT cos 2 pi FCT. You are representing error and noise in terms of in phase and quadrature phase component. So it is NI cos 2 pi FCT and includes sin 2 pi FCT. Okay, yeah. So then this will be again multiplied with cos 2 pi FCT. That is the output of a product modulator V of t, right? And then pass it through a low pass filter. So if you again multiply this with cos 2 pi FCT, that is X of t into cos 2 pi FCT. So you are multiplying each term of this with cos 2 pi FCT. So you will have here one cos 4 pi FCT term and one cos 0 term. And here also you will have one cos 4 pi FCT term and one cos 0 term. 1 by 2 will be there. And here you will have sin 4 pi FCT term and then sin 0. So that term will be 0. So you are having, you are separating your term like this, half CAC M of t, half NI of t, and your cos 2 pi FCT term and sin 2 pi FCT terms you have separated. So this terms, terms will go off in the low pass filter as you pass it through a low pass filter, because they are at frequency 2 Fc. This is sine frequency at 2 Fc. Okay, so this sequence will be removed by passing it through a low pass filter. And so the output of the low pass filter, you are having only these two terms, that is half CACM of t and half NA of t. Okay, yeah. Rita, this is your S of t is a modulated signal and noise. This is your received signal X of t, and the X of t is again multiplied with the cos in your receiver, and that you are denoting it as E of t. Then it is passes through a low pass filter. So you are getting only this CAC M of t by 2 and half N of n of t. So what is the inference you're having here is Ni of t, right? You're having only the in phase component. So what is the inference you're having is the output of the demodulator, you are having a message term and it's added with the potential component of your narrowband noise. Right, so you can find the message power and noise power separately. So the receiver output, you're having the message component. So your message power is you're having CAC M of t as a message signal. CAC equal to M of t. So message power pakana is C square AC square by 4. Just you are squaring. The term is squaring C square AC square by 4. And then half Ni of t. So you have to find the average power of your in phase component. So the in phase component average power will be same as the average power of your narrowband noise N of t. Already you have studied in narrowband noise that the power spectral density of in phase component is equal to the power spectral density of quadrature phase component, and the power spectral density will be given as Sn of f minus fc, Sn of f plus fc, right? So it will be 2 Wn0. So if you find the average power of noise at the receiver output, it will be 1 by 2 Wn0, and so if you find a SNR O, that is the output signal to noise ratio of your DSP-SC, it will be C square S square by 2 W A0. And if you find your figure of merit, so SNR O and SNR channel, here you have find the SNR channel value, and here you have find the SNR O, both are same. So you are obtaining the figure of merit as 1. So for the DSP-SC receiver, you are finding the figure of merit as 1. So what you are doing is you are analyzing the circuit by finding the signal power at the input and that is modulated signal power and the noise power. That is in this place you are finding your this is S plus N, S of t plus N. So you are finding the modulated signal power and the noise power and finding that ratio, that is SNR input, and you are finding SNR channel is your signal power by noise power in the message bandwidth, and then you are finding the SNR O. So, and you are finding the ratio of SNR O and SNR channel to get your figure of merit. Okay, so the figure of merit, you are finding it to be a value 1. So, figure of merit values more means that the performance is good. So, this is a noise in AM receiver. The same way it will be followed, and it is fine that your figure of merit for AM receiver will be a value less than 1. All right, it is given as k square p divided by 1 plus p square p. So, which is the value less than 1 because your denominator is more than the numerator. So, your SNR of AM receiver will be less than 1. If you take a single tone frequency, your SNR value will become 1 by 3. Right? So, the figure of merit for AM receiver, if you take a single tone. This is your general equation. K square p by 1 plus k square p. Instead of p, if you substitute a message am square by 2, then you will get it as mu square by 2 plus mu square. And if mu is equal to 1, you will get it as 1 by 3. So similarly, noise in FM receiver, same procedure you have to follow. But here you are having limiter, discriminator, and then a low pass filter. This will go with some derivations. And finally, your figure of merit will be derived as 3 square p by w square, right? So this is the figure of merit for FM modulation. So from this, what you have inferred is this the kf is equal to del f into am, which you have already studied. Kf is frequency sensitivity. So kf is equal to del f into am, and del f by w is nothing but deviation ratio. That is modulation index beta and Fibonacci, and similarly deviation ratio. So your figure of merit is proportional to d square. And if you increase the bandwidth, your performance will be better in frequency modulation. Similar to AM, if you use a single tone, then your value will be, you are getting it as 3 by 2 beta square. And for AM modulation, you are getting it as 1 by 3. And for FM modulation, your value is 3 by 2 beta square, so which is more than the other modulations. So 3 by 2 beta square should be greater than 1 by 3 to make your FM better than your AM. Right? So your beta value should be root 2 by 3. And that is the transition between narrowband FM and wideband FM, because your narrowband FM signal is similar to your AM signal, except your sideband polarity reversed. அதெல்லாம் நீங்க ஆல்ரெடி படிச்சிருப்பீங்க AM signal, FM signal. So here you are only analyzing your noise performance. So what is the inference you got is usually noise performance in FM receiver will be better compared with noise in AM and DSP. That obviously you know, because the FM signal amplitude is constant. So noise performance of FM system will be better than your AM system. Full AM system and as well as DSP-AC system. And if you compare AM and DSP-AC, your DSP-AC system noise performance better than your AM system. So as for this unit concerned, you are having types of noise, and then you should know what is meant by narrowband noise. Before that, you should know what is meant by white noise and what is meant by narrowband noise, and how to represent your narrowband noise in terms of your in-phase and product-to-phase component, and how to represent your narrowband noise in terms of envelope and phase components. Then to study about the noise performance of an AM receiver, DSP-AC receiver, and FM receiver. We are using the ratios, that is SNR input, SNR output, and SNR channel. Usually SNR output and SNR channel is used for finding your figure of merit. So from the figure of merit, you are concluding that the performance of your FM system is better than the performance of your AM system and DSP-AC system. So that's all about noise performance. Thank you all. So if you have any queries, you can ask.
Thanks for the wonderful session, ma'am. It was very knowledgeable and insightful information. This will be enhanced knowledge in random process and noise in communication system. Now we have come to question and answer session. Kannamma will take over the question and answer session. Over to you, Kannamma.
Thank you, Ms. Anita. Thank you, ma'am, for the wonderful session and interesting presentation. I have shortlisted a few questions from the chat box, ma'am. The first question is, can random variable will be in negative?
Can random variable?
In negative.
Yeah, you are assigning a random variable means you are assigning the output of a random experiment to your real numbers. It can be negative. That is, if you take an example, as I told, tossing a coin, head and tail are the outcome. So head can be assigned to -1, head can be assigned to +1, tail can be assigned to -1, or anywhere return.
And the next question is, what is the difference between Gaussian noise and white noise, ma'am?
So there is no white noise is not necessarily it should be a Gaussian noise, right? The white noise is not a physically realizable noise. So you are modeling a noise for a communication system that a noise is affecting all frequencies equally, right? So if it is having the Gaussian distribution, the white noise, having the Gaussian distribution, you are calling it as a white Gaussian noise, right? So if the noise is having the Gaussian distribution, that noise you are calling it as a Gaussian noise.
The next question is, what are the application in wireless WSS random process through LIT system?
See, that is you are passing a random process through a system and analyzing, and you are finding the power cycle density and autocorrelation and all. That's the thing you are using in analyzing communication system. Even if you take a FM system, you are deriving that if you go through that noise performance of an FM system, you will be analyzing how the noise is coming out of a system and what will be that power cycle density. So from the power spectral density, you are going for an average power, right? So you want to analyze the receiver system, and take for an example a FM receiver system. So in the FM receiver system, you are having a limiter and then a discriminator circuit. So in that is nothing but a system. So you are analyzing how the noise getting in and coming out. What will be that output noise power? So to calculate the output noise power, you need a power spectral density, which will be easy for you to calculate. Just integrate your power spectral density curve, then you can find the noise power. So in analyzing all communication systems, you have to understand you are passing a random process through a system. I think, is it clear?
Yes, ma'am.
Is it clear?
Yes, ma'am. Yes,
Okay,
ma'am.
ma'am. Yes,
Okay.
ma'am. Kanama, next question.
Yes.
Namo?
Ma'am, we read out the question, madam.
Yes. Yes, ma'am.
Ma'am, what are some real life applications of power spectral density?
So that's what I told now. You are analyzing a system means you need a power spectral density to find out the power of a signal, average power of a signal. So the power spectral density is nothing but the graph showing the power with frequency, the power spectrum. It is nothing but the power spectral density. So if you take a random process in communication, you are usually facing with your random process, that is random signals. So in order to find the average power of a signal, you should know the power spectral density. So to analyze.
Ma'am, the next question
Okay,
is,
ma'am.
what are some...
Yes.
Kanama, I am reading out the question since you are
Okay,
not
ma'am.
audible. Okay. Next question is, ma'am, provide the real-time examples of ergodic process.
Real-time example of a ergodic process, that is actually if you take a real-time examples of a random process, you can tell. You have to analyze whether it is ergodic or not by only analyzing, that is taking that random variables. So for an example of a real-time random process, you can take even your signal, as I already told, your communication signal is random, and suppose you are measuring the temperature, your stock market, or your analyzing a digital communication system, the number of bits received in error, everything is random. So it is a random process, right? So in that a random process, whether it is ergodic or not, you have to pick up that random variables and then analyze it. So if you take a random process group, and in that you are making it as some processes triple S process, that is strict sense stationary process. So all audio disturbing, ma'am.
No, ma'am.
Uh,
No, ma'am. You continue, ma'am. Your voice is
okay.
audible.
Okay. All the strict sense or will be wide sense, but all not wide sense are strict sense. So you are confining it to wide sense இருந்து இன்னும் கொஞ்சம் stricter rules போட்டோம்னா triple S வருது. அந்த triple S ல you are framing still more rules, right? That is your time correlation should be also equal to your ensemble average. So you are restricting the random process. The ergodic you are limiting, putting more conditions on that. So whether the process is ergodic or not, only you can analyze the random process and decide it.
Okay, ma'am. The last question. Many questions have been posted. I will send it and get it clarified from you. The last
Okay.
question is, what are the drawbacks of using a DSB, SB, SC signals? What
is
are
the
the
drawback?
drawbacks of using
Um,
DSB, SC signals? I
that
think
is
Lalita has
DSP
posted
SC,
this.
double sideband suppressed carrier signal, right? So DSP
Ah,
SC signal, say, if you see the modulation schemes, you are having AM modulation and then DSP SC modulation, that is suppressed carrier modulation. So comparing your AM and DSP SC, actually DSP SC will be better than AM modulation, right? So if you go for AM modulation, the DSP-SC is having power saving compared with AM. AM is having one carrier, one upper side and lower side. But DSP-SC is having only upper side and lower side, and there is no carrier. So mainly from AM, why you are going to DSP-SC is to have an advantage. So it is having power saving. But when you compare with the other modulation like SSB, it is having bandwidth more, right? The SSB will have less bandwidth compared with your DSP. So going for AM modulation for a particular applications. So if you prefer, you will be preferring DSP only, right? Since it is power saving. But for
okay, ma'am.
if you're concerned in bandwidth, you are going for SSB modulation.
Okay, ma'am.
Okay.
Thank you so much for answering all our queries. Students have posted some more queries also. We'll be sending in mail and get it clarified.
Okay.
Over to Anita.
Thank you, ma'am. Let us be grateful to people who make us knowledgeable and happy. They are the charming gardeners who make our souls blossom. May I call upon Ms. Darshini to deliver the vote of thanks. Over to you, Darshini.
Thank you, Ms. Anita. Good evening, everyone. Respected and most distinguished chief guest, respected principal, our beloved vice principal from HOD, our professors, and my dear friends. I deem it a great honor and privilege to propose a vote of thanks for today's webinar. Let me first of all giving glory to Almighty God for making today's webinar a resounding success. Now I would like to thank our speaker, Dr. K.R. Shanti Ma'am, Associate Professor of ECE Department in KLN College of Engineering, for visiting and enlightening us with her knowledge. Today's webinar was full of knowledge and interesting things. It gave deep insight to the topic and also revealed some interesting facts. The information that ma'am told us about random process and noise characterization in communication system was really informative. I am pretty sure the precious knowledge that ma'am gave us will definitely help us in our studies and future. Once again, I would like to thank Dr. K.R. Shanti ma'am for taking out time from her busy schedule and enlightening us with the knowledge. And beyond the content, we have got more courage to face the exam with much confidence from your presentation in spite of faculty, and you have improved our confidence level to score more marks. Thank you so much, ma'am. The value of college education is not the learning of many facts, but the training of mind to think. So I would like to thank our respected principal, Dr. Sujata Anand ma'am, and my sincere gratitude to our beloved vice principal from HOD, Dr. L. Nalini Joseph ma'am, for her support and bringing out the speaker for this wonderful session, and my heartfelt thanks to the faculty coordinators who helped us with proper guidance and support. And I also want to thank the student committee who really worked hard to make this event successful. I heartily congratulate all the participants for their active participation in this event. No program can be successful with a single person. So I extend my big thanks to our department, and on behalf of our student coordinators, I thank our department staff and students for their support. Once again, I thank you everyone who are all gathered here and made this event a successful one. Thanks a lot. Over to you, Ms. Anita.